So I'd like to introduce Eugenie Euskirchen from the Institute of Arctic Biology, Department of Biology and Wildlife, for the first Earth System Science seminar.
Okay, thank you, Carl. Thanks all of you for coming and signing up for class. Yeah, so today I'm going to be talking about permafrost carbon and the global carbon budget. This is a topic I've been working on, well, ever since my PhD, really, and I've been really into it since I began at UAF in 2004. So, let's see. There we go. Okay. So I want to first go through a little outline so you know where we're going today, and then I'll start going through what's in each of these bullets here. So I want to first start off and talk about carbon dioxide in the atmosphere, where we are now and where we've been in the past, and where we're probably going, and then also think about how this relates to our remaining carbon budget, how much more carbon we can emit into the atmosphere before we reach a certain point of warming in the world. And then I want to talk about permafrost carbon and how this then impacts what we call the remaining carbon budget. And I'll tell you what the remaining carbon budget is. And then finally, I want to go into some more case studies and talk about some work that I've been doing here closer to Fairbanks in the interior lowlands of the Tanana Flats, and how we've been looking at carbon cycling there for quite a number of years now. And then I want to think about not just site-specific studies, but how do we think about scaling up our work into the whole Pan-Arctic? So to get started, here's the graph of carbon dioxide over the last 800,000 years. This was put together through ice core data. And you can see here that at 2024, we were at 422.8 ppm. And that's in that little pink line there. It looks like it's almost an instantaneous increase in the modern data. It goes from about 280 ppm to over 400 ppm, it looks like, within the course of a year. But really, when you span that out across 800,000 years, that's actually over the course of about 100 years that we've had that increase. The previous highest level over the last 800,000 years was about 300 ppm. And so we're higher than any point we've ever been. We'd have to go back really far into the past to reach points where we've been previously. We'd have to go back about 2.5 million years ago. And this is, again, a graph that's based on reconstructions. This time it's based on deep sea sediment data from the oceans. And you can see that once we start going back millions of years, it gets a little fuzzy. There's a lot of a wide range in the data there, illustrated by this blue blue area between the two gray lines. That's the range based on this sediment data. But either way you look at it, we'd have to go back about 2.5 million years to get to a level of carbon dioxide that we are seeing at present. And so at that point, 2.5 million years ago, temperatures were about 2 to 3 degrees warmer on Earth than they are today. And this is a time when there were camels on Ellesmere Island. So Ellesmere Island is in the high Arctic. They were roaming in the boreal forest amongst the larch trees. That's what this tree here is. It's a nice larch, turning like it is around now here in Fairbanks, so nice, pretty yellow. So it was a very different world back then when we had the same level of carbon dioxide in the atmosphere that we do now. Where are we now in terms of warming? So since pre-industrial times, we've seen about a 1.1 degrees Celsius increase in the global average of temperature. And so there's some areas like the high latitudes that have seen a much larger increase in this temperature, and then some areas that have seen a little bit less. But if you average it out across the globe, it's about 1.1 degrees Celsius warming. And it's about a 0.4 degrees C increase, or 0.2 degrees C increase per decade. So it's a lot of warming, particularly in the high latitudes, where it's about 4 times more than the global average. And so this leaves what we call a rapidly shrinking carbon budget to stay within the aspirational limits of the Paris Agreement. And the Paris Agreement on climate change is a global treaty to try to limit the amount of greenhouse gases. Each nation says how much they would like to contribute to lowering their greenhouse gases, and they every few years put in a new plan saying what they will do to lower greenhouse gases. Of course, the US is no longer a member of the Paris Agreement with this current administration, but we were up until recently. And so the aim here then is to keep global temperatures at preferably 1.5 degrees C warming, no higher than 2 degrees C warming. The Intergovernmental Panel on Climate Change has a whole report on the differences we'd see on Earth in a 1.5 degrees C versus 2 degrees C warming, and there's quite a range of extremes that can happen within that, just that 0.5 degree Celsius temperature warming. So to think about the global carbon cycle, we put together estimates of how much carbon we've emitted into the atmosphere and how much we've taken up through the land and the oceans. And so each year, the Global Carbon Project, which is a consortium of scientists from many institutions around the world, works on this global carbon budget, and they put out what they think is the best estimate for that given year. It usually takes about a year for it to come out. So this is based on the global average for the decade between 2014 and 2023. And this is all in gigatons of carbon, which is 1 billion metric tons. I know it's hard to think in these large terms, but 1 ton of carbon equals 3.67 tons of carbon dioxide. And so we're emitting through anthropogenic fluxes over here about 35.6 gigatons of carbon per year average between 2014 and 2013. And then some of this is naturally taken up by the vegetation and the soils. And then also in the ocean is also considered a very large sink of carbon. But then there's some more that's also emitted through land use change, and that's mainly due to deforestation in the tropics. And you can see here, this is actually a fairly new addition to the global carbon budget. We have in the soils, we have this circle, which is a pool of permafrost. And interestingly, you can see here that there's no number above the permafrost. What are the emissions from the permafrost soil? So the global carbon budget has left that kind of blank for now, it seems. And we can look at this in another way. We can put the sources of carbon dioxide on one side and the sinks on another. And so the sources, like I just said, from fossil fuels and industry, about 35.6 gigatons of carbon per year. And we get this data from energy production statistics and also cement production. Cement actually, production of cement emits a large amount of carbon dioxide because a lot of times it's using limestone where there's a lot of carbon. So that's about 90% of our emissions into the atmosphere are fossil fuels and industry. And then this land use and land cover change part is about 10%. And like I said, this is from deforestation in the tropics. And we keep track of this through bookkeeping models where we study the amount of carbon in the soils and the plants prior to deforestation and then also afterwards. And from that, we get about 4.1 gigatons of carbon dioxide released per year. And then the sinks. This is a lot of carbon just goes right into the atmosphere and hangs out there, and that's what causes the warming. So we get this through measuring concentrations of CO2 in the atmosphere and then looking at how those concentrations change annually from year to year. And so this is about 48% of our sinks. And then we have the land and the ocean sinks, which are very good at taking up carbon dioxide. And we estimate these through global process models that are constrained by field data. And so when you add up the sources down here, you get 39.7 gigatons of carbon per year. And then you add up the sinks, you get 41.4 gigatons of carbon dioxide per year. And so considering everything that's involved in getting these numbers and these estimates of the sources versus the sinks, you say to yourself, wow, that's pretty good. That's only a 4% difference in the sources versus the sinks. It's about a difference of about 1.7 gigatons of carbon dioxide per year. But it's not so simple as that. This is a graph of the budget imbalance. And so that black line in the graph, that's the 4% I was just showing you from year to year on the previous slide. But then you can see that there's this red shaded area all around that black line, and that is the uncertainty across all the various sectors. So each of those sectors, when we estimate the amount that's going into the atmosphere or going into the land and the soils or being emitted, that's subject to all sorts of error and uncertainty, because it's really some very complicated methods that we use to get those numbers. So there's a lot of uncertainty going into this. And like I said earlier, permafrost is not really known, and that is also kind of considered within this uncertainty, but not really. So we have what we call then the remaining carbon budget. So this represents the total amount of carbon dioxide that could still be emitted in the future, while we're limiting global warming to a given target. And so in this case, 1.5 degrees C warming average across the Earth. So between 1850 and 2024, we've emitted about 2,700 gigatons of carbon dioxide total. And then between 2025 and going into the future, if we want to stay within this 1.5 degrees C warming, we're only really allowed to emit between 100 and 500 more gigatons of carbon dioxide over the next 7 years. And so if you think about that in relation to everything we've already emitted and our current rates of emissions, it's not really that much that we're allowed to emit before we overshoot our temperature goals. And so that's nicely illustrated again here. So our 2024 emissions were about 37.4 gigatons of CO2 estimate. And then we say that we have about, say, 340 gigatons of carbon dioxide still allowed to emit. If we want to reach our targets, we need to reduce this by about 65% by 2030. And then by 2040, we need to actually have net zero emissions. And so right now, well, this is a little older graph. It's back in a few years ago. They say we have about a 67% probability of meeting this 1.5 degrees C warming target. And I would probably say a little bit less than that now. So now that's just an overview of the global carbon budget and where we are and where we want to go and how the various sources and the sinks work and all the uncertainty that's wrapped up in that. And so to further go into this uncertainty in the global carbon budget, I want to turn to permafrost and permafrost carbon. This is a map of permafrost over the Arctic. So you can see here there's areas of continuous permafrost that are mostly concentrated in the north. And then as you move south, you get into regions of discontinuous, isolated, and sporadic permafrost. And so this permafrost, it's built up over many thousands of years or millennia, and it's contains about 1,700 billion tons of organic matter. And so this is, remember what I just said, how much we've already emitted into the atmosphere, about 2,700 gigatons of CO2. It's about 4 times the amount that we've emitted by humans in modern times. And so I should also say something interesting here too, that this map is of the permafrost region. It's only 15% of our soil area on Earth, but it's actually 1/3 of the total soil carbon on Earth. So it's a small part of the Earth, but it's very significant. And so how does this work from a process based? How is carbon dioxide released and methane released from the permafrost? So historically, you have over here, you have permafrost, and then above that you have the active layer, and the active layer is the area of the ground that freezes and thaws on an annual basis. And so it's typically been about this deep, but then under warmer conditions, there's more area of the permafrost that's freezing and thawing annually. So it's deepening. We call this a deepening of the active layers. It goes down into the permafrost. And so as this happens, there's two dynamics to think about. There's the dynamics during the growing season, and then also during the winter season. So during the growing season, the microbes are there. They're breaking down the plant organic matter, and it gets emitted into the atmosphere as both CO2 and methane. But at the same time, the plants are growing, and as the plants grow, they of course photosynthesize, and when they photosynthesize, they take up carbon dioxide. But then the plants grow and they also decay, and then this decayed plant matter returns carbon to the soil as a pool to potentially stay there. But then winter comes along, and of course the plants are no longer growing, they're senesced, they're not taking up CO2. But interestingly, the microbes that live in the soils, they can remain active all winter long. They're groups of soil microbes that are active in the winter. And so as the winter lengthens, particularly in terms of the time it takes for the soils to refreeze again, the plants are senesced, but the microbes are still emitting carbon dioxide and methane into the atmosphere for long periods of time under warmer conditions. So there's this potential increase in microbial decomposition during the winter. And so the question then for people who study these things is, what is the magnitude, timing, and form of carbon release to the atmosphere in a warmer world? And this is a question that has been fluxing scientists for at least a decade now. It wasn't a very big issue about 10, 15 years ago, but it's become a much larger issue as we've begun to realize that the soils are warming a lot faster than we thought, and that the CO2 and methane is getting released faster than we thought. So for a long time, at least 20 years, we've been able to model what the permafrost looks like currently and what it may look like in the future. So this is a model simulation I did. So it was published in 2006, and so that meant I did this simulation back in 2005. So 20 years ago, we were able to say, okay, so this is what the permafrost looks like today. This is what the permafrost looks like by 2040 to 2050. And then if you take this map B and you put it on top of map A, you can see that there starts to be little areas around the southern borders here, the pink areas where the permafrost has thawed out. And then 2090 to 2100, we estimate that the permafrost region looks like this. And we put that map on top of map A, and you get a lot more of the pink region poking out. So that corresponds to permafrost loss, about 600,000 square kilometers of permafrost loss by 2100. But then the question really is, okay, so we're losing this permafrost, and that has all sorts of issues, but what's the real issue in terms of carbon dioxide and methane coming out of that permafrost that was thawed? And so our current understanding of these dynamics are not really are not really great, and they're not at all reflected in any sort of policy dialogue. Right now, our estimates of permafrost thaw and release of greenhouse gases, CO2 and methane, they're really a really wide range right now, from 22 gigatons to 432 gigatons of CO2. That's a huge range. And so this is under gradual permafrost thaw and strict mitigation policies for climate warming, where we only get up to 1.5 degrees C warming. So this is a pretty conservative estimate and very wide range. If we have weaker strategies where we allow the world to warm more than 1.5 degrees Celsius, we get up to 550 gigatons of carbon dioxide released. And then, to make matters more interesting, both of these estimates are really underestimates, because we don't really have a very good way of modeling or estimating abrupt thaw. What happens if things just thaw all of a sudden instead of this more gradual thaw that we incorporate into our models? And also, we're still trying to understand the effects of wildfires on permafrost thaw. How do increases in wildfire severity, for example, impact permafrost? And so there's a lot of uncertainty. And then I also want to remind you that in the previous slide about the remaining carbon budget, we said that we had about 130 to 500 gigatons of CO2 that we're allowed to emit to mitigate warming to 1.5 degrees Celsius. But our estimates of CO2 release from permafrost thaw alone are potentially in line with that or much larger. So it's a significant unknown in terms of the global carbon budget. And so how do we study this? How do we get better estimates of these losses of carbon? So what do we need to consider? And how do we measure them? what's the interannual variability of carbon exchange? So we can go out and we can make measurements for a year, but is that really all we need to do? Is 1 year going to tell us everything we know about CO2 and methane loss from a permafrost ecosystem? How does it change if we say have an extreme warming event or an extreme drought or rain on snow? How does this impact the losses versus just long-term warming trends? And then there's this idea of landscape heterogeneity. If you go out and you walk around the tundra or the boreal forest, it's not all just trees, it's wetlands, and it's different types of wetlands, and it's different types of tundra. Some are wetter and some are drier, and some have isolated permafrost and some have thawing permafrost. So we have to take all this landscape heterogeneity into account. And then on top of that, we want to not just study this at the site-specific scale, we want to upscale it to the whole Arctic so that we can understand what's going on as a whole. And so there's been a number of studies, as you can imagine, that have tried to get at the matter. This is just a summary of a few of them, going back about 12, 13 years. In 2012, Dave McGuire, a former professor at UAF, retired now, published a paper and based on synthesis data and modeling. And he said the tundra is a sink of carbon dioxide and actually a small source of methane. But then in 2013, there was another synthesis that came out and said, nope, the tundra is a source. 2019, 7 years later, nope, it's still a source, but the source is actually larger than previously estimated because before we weren't very good at taking into account these winter emissions. And if you take these into account, then the emissions are going to increase. 2021, the boreal region is a strong sink. We've always thought the boreal region is a sink. The tundra has been maybe a little more questionable, but then maybe the tundra here is a slight sink to a small source. And then more recently, non-permafrost boreal ecosystems are increasing as a carbon sink. Boreal and tundra ecosystems with permafrost are actually losing more carbon. They're not maybe sources yet, but they're becoming sources. And then a year later, nope, we need to consider wildfire emissions too. And when we consider this, then the non-boreal permafrost ecosystems are not in an increasing sink, and the permafrost region is carbon neutral. So there's been this whole discourse in the literature on the carbon sink strength of the boreal and tundra ecosystems. And we're still, as you can see, here's just 2025, we're still trying to figure it out. So my small contribution to the puzzle has been to make long-term measurements, both in the boreal and the Arctic tundra ecosystems. Today, I'm just going to talk about some of our measurements in the boreal area. This is very close to Fairbanks. It's part of the Bonanza Creek experimental forest. If you drive down the Parks Highway about 15 miles from UAF, 10 miles even, you'll get to a gate and off the Parks Highway that you will probably usually just drive right past. But if you go around the gate, you'll drive down a very bumpy and muddy road, and you'll get to my field sites. And so we established these sites in 2010, although the data collected at these sites goes back to 2004. There are 4 sites that are across a gradient of permafrost thaw. They're all in close proximity to one another. They're all within about 1 kilometer of one another. And so we have a black spruce forest. And when we set this up, we thought, okay, this is a great place. It's got very cold soils and stable permafrost. We compared the soil temperatures to other black spruce forests around the area. And there were some of the colder soils that we measured, if not the coldest. And so we thought that was great. And then we set up a site in the Thermokarst bog. This is an area where the permafrost thawed about 100 years ago and is continuing to thaw. And then we also set up another site a little more recently in 2018 in an older Thermokarst bog. This actually thawed out about 500 years ago as we came out of the Little Ice Age. And then we have rich fen, and this has actually no near surface permafrost, but it has a groundwater table that's connected to the nearby Tanana River. The difference between a fen and a bog is that the fen has groundwater dynamics and a water table that's connected to other sources for receiving water inputs, whereas a bog is closed off and the only inputs of water it receives are as precipitation. So we started collecting this long-term data of carbon dioxide, methane, and energy and water fluxes with the question of what are the carbon sink source dynamics and what's driving them. We use a method called eddy covariance. And so in this method, we set up instruments that include a sonic anemometer. That's this thing with the little claws on it. And that is measuring the eddies in the air at a very fast speed of 10 times per second. And then we also have over here this infrared gas analyzer that's measuring CO2, methane, water, energy fluxes. And so we determine how many molecules go up with the eddies at time 1 and then how many go down at time 2. And then from that estimate, we can calculate a vertical flux at that point in time. And then we're doing this typically in units of micromole CO2 meter squared per second. And then we do this over a long time and we can calculate carbon flux over years, months, days, whatever time period of interest we're interested in. And all this, of course, happens very quickly. So net ecosystem exchange, it's what we're collecting in terms of the CO2 data. It's the difference between gross primary productivity, which is all the photosynthesis in an ecosystem, minus heterotrophic respiration. So that's what the soil heterotrophs are up to in terms of decomposing the soil organic matter, and then the autotrophic respiration or the plant respiration. So when you subtract the gross primary productivity from the respiration, you get a net carbon uptake or release. And so this represents the CO2 balance of the land. We say that a negative NEE, a negative value of CO2 represents a sink, and a positive value represents a source of CO2 into the atmosphere. So based on all our data collected over this time, we've seen some interesting dynamics in terms of the climate and the changing here. We see since 2014, we had record rainfall, and pretty much every year after that, except for 2022, I believe, we've had above average rainfall in these sites. And most years we've also had above average snowfall too. So there's been this overall increase in precipitation, which if you are familiar at all with global climate models, this is actually what they estimate. They estimate that we'll see more rain and more snow. But despite the fact that we've seen this increase in snow, so this increase in snow water equivalent down here, a significant trend, the duration of the snow season has actually shortened. And this is due to the day of snow return has gotten to be significantly later around Fairbanks based on the data that we've collected since 2005. And then the day of snow melt, there's no significant trend. And then we've seen some really interesting dynamics in terms of the fen. We've seen some changes in the water table depth. So most years prior to about 2011, we actually saw the water table depth at the fen was below the surface. And so it was a much drier area. But since 2012, we've seen many years where it's just outright flooded. And it's turns into more of a lake than a very dry fen. And so here's what the fen looks like when it's dry. It's a very pretty sight. There's all sorts of green grasses, and you can walk in it fairly easily without sinking. But when we have the flooded conditions, we're actually reduced to using boats to get around. It's a little more like a pond. So there's been this really extreme variability at this site in terms of the water. And some of it's related to these increases in precipitation we see, and some of it we're still trying to figure out. Maybe it's more water from permafrost thaw. This is a slightly lower elevation than the black spruce forest, just a few centimeters, but as permafrost thaws, it can create more water that floats into the fen. And then also these ground table dynamics, groundwater dynamics with the nearby Tanana River. And so the soil temperature at both of our spruce and our fen sites has increased significantly over the winter, and at the bog it's increased significantly in the fall. And while I was showing you how the fen can be much wetter since about 2012, we also see increases in soil water content at the bog as well that are statistically significant. And then this is a graph of the depth to permafrost, and by that we mean essentially the active layer. And based on all these different measurements between the bog and the forest towers, we see that there's an overall increase in the active layer depth, indicating that the permafrost is thawing. So remember I said we chose the black spruce site because we thought the soil temperatures were very cold and it was very stable permafrost. But in reality, we're starting to see areas of thaw around the instrumentation in the black spruce site. And so what do the dynamics of carbon dioxide and methane look like? All these ecosystems are actually sources. So like, remember I said a positive value of NEE is a source of carbon dioxide or methane into the atmosphere. So methane emissions here are highest, methane and carbon dioxide emissions are highest in the fen, partly because of these increasing wet years. They're also pretty high in the bog. The black spruce is a fairly dry ecosystem, so we don't see a lot of methane. And so actually, you can see here the green line, the light green line here is carbon dioxide, and then the darker green line is carbon dioxide and CO2 combined, and they're almost right on top of each other, which meant there wasn't much going on in terms of methane emissions from the black spruce forest. And so we decided that was very boring to keep measuring, and we then took the methane sensor off the black spruce site, and we started up this new site at the old bog in 2018, and we added a new carbon dioxide sensor and the old methane sensor to get estimates of carbon dioxide and methane in the old bog as well. And so this is a significant source too. So all these ecosystems are sources of carbon dioxide, black spruce a little bit less so, the fen the most. And it's interesting because the fen is actually the area, is actually the ecosystem type that we think is increasing the most in this region. So we think that sometimes these bogs turn into fens as the permafrost continues to thaw, and then sometimes the black spruce can just immediately turn into a fen once the permafrost thaws. So this is a landscape feature that we see that is increasing the most, and it also has the greatest amount of greenhouse gas emissions. And so then we did a little bit of back of the envelope regional scaling to see what if we take the percentage of these ecosystem types that are on the landscape and estimate the release of carbon dioxide and methane across the interior Alaska or just across the Tanana Flats. And then we played around a little bit with the percentages of each. So this is what we have now. We said that fens cover about 40% of the landscape, bogs 7%, and spruce about 24%. And so this is our estimate of carbon dioxide and methane release based on upper and lower bounds and also our data. And then we'd have to essentially increase the spruce by about 50%, the black spruce to about 50% of the landscape if we want to see any significant reduction in greenhouse gas emissions in the boreal lowlands of Alaska based on these ecosystem types in our measurements. So it's a much stronger source of CO2 and methane than we originally thought. And we're not very good at modeling this. It's very hard to go out and delineate bogs versus fens at a landscape level. And also, we don't really often think about the impacts of changes in precipitation. If you go back and read the paper that this was all published in, you'll find out that part of the reason we see these big increases in emissions is due to this change in the precipitation regime we've seen since 2014. So I think I just said most of this. Yeah, and sometimes you might hear the in the news, if you follow it, talking about how maybe Alaska can start selling like carbon credits and stuff because we're taking up all this carbon dioxide and methane in our natural ecosystems. Well, this no, we're maybe not. This is not a carbon offset at all. It's a source. So I think maybe they haven't quite done their homework there, but just something to keep in mind if you read that in the newspapers. So now I'm going to switch gears, and why am I showing you this graph of sea ice? I'm not going to go into sea ice, but I want to show you this because, see, look, I downloaded this just 2 days ago on the 3rd of September, and we have this beautiful line showing where, well, it's not beautiful, the sea ice is decreasing, but we can see how it's decreasing, and we can see that on pretty much a daily basis, and we can compare that to these very long-term data sets going back to 1981. So this data is updated daily with a 1-day lag. On occasion, there's a data delay, which might be resolved within a few days. And so this, of course, is all collected via satellite data. And so it's, it's not like it's a piece of cake to do this, but they can, with some effort, make these things available on a very frequent basis. So we just can see what exactly is going on. And so then, wouldn't it be great if we could do this with carbon, right? And see what's happening in the permafrost ecosystems and how they're changing on a daily basis in terms of their carbon uptake. Well, we can't actually do that. We don't have satellites that can look at net carbon uptake. We do have satellites that can look at carbon dioxide concentrations and a little bit of, say, gross primary productivity, but they're pretty bad over high latitude regions. And they don't have data going back all the way to 1981. They're a little more recently launched. So how do we even begin to do this to get to more of an instantaneous measurement? The papers that I was talking about earlier, the ones even that were just published in 2024 and 2025, the data that go into those, they're already about 4 or 5 years old by the time the paper is published. So it's already out of date by the time you read it. And so what I'm showing you here is a distribution of sites that contain eddy covariance towers, or sometimes chamber measurements, all across the Arctic. Some of these are just operating during the summer. Some of them operate year round. But you can see that there's a fairly good distribution. There's some areas where we lack measurements, but in general, we have a lot. We're pretty well off in Alaska and parts of Canada. Of course, Siberia is, well, it's a no-go zone right now, and it was already sporadic to begin with. But what if we were to take this data from our measurements and think about putting them together at a more instantaneous time scale and summarizing them? And so that's what some of us have started to do. We've started to process our data at a very regular basis and then synthesize them. And this has been put out last year in the Arctic report card. So we had a section on Arctic terrestrial carbon cycling. And we were able to take, so you saw that on the map, there were a lot of sites, but we were able to get about 19 sites together that were able to process their data in time for the Arctic report card to come out in December last year, and say what was going on with these representative sites from across the region. And it's interesting, you can see here that 2024 mean, actually, we see more of a carbon release than we do of a sink. And we were able to say that with some degree of certainty. And now we're trying to get ready to do that again because it's August. And so you can see here this ends in August of last year. And so it's, well, September now. We try to get our data processed by the end of September so that we can, again, put something out like this. But like I said, these things are easier said than done. We don't have satellites. This is a photo that my colleague Oliver Suttentang just sent me yesterday. He said he was hoping to process his data, and then his site is in a remote part of Canada, and he went out to a site, and this is what happens when a bear visits your instruments. So unfortunately, we won't be getting data from him. His instruments will be back getting repaired instead. And then this is actually our site this past summer, the Bonanza Creek area. You may have heard about the Bonanza Creek fire. And so this is from our webcam at our bog site. You can see we looked at this and we thought, oh my God, our sites are going to go up in flames, any day. And thank you to the firefighters, and they knew about our sites. They put in a very good containment line that kept the fire away. But at the same time, we weren't able to visit our sites, and one of our methane sensors was non-functional. So it remained non-functional all summer because we couldn't fix it. So there are lots of problems that go into trying to provide data at an instantaneous level, especially when you have these remote sites that are trying to operate year round. And so finally, just to conclude, measurements need to be long running and take into account the full annual cycle so that we can get these winter respiration measurements and also all this spatial heterogeneity across the landscape. We need to think about not only temperature, but precipitation and changes in the water regime as well. We need to fill in areas with sparse measurements, although in some places like Russia, that's never going to happen. And then we need to make data as soon as possible, the data available as soon as possible, so that we can really start to understand what's going on from year to year in terms of the carbon budget and permafrost ecosystems. And then models still have some catching up to do too. They're not very good at thinking about landscape heterogeneity. They sometimes have problems with winter estimates of CO2 and methane emissions. And they also need to work towards comparing against our long-term measurements as well. And so that I'll just say the permafrost carbon feedback is important. You guys have a question?